Um, okay, let's see. I heard something. All right. So in some sense, what is going on here is, this is sort of the world we live in. And, it's kind of strange, but this counterfactual world is an abstract world that sort of gives us a way to kind of define treatment effects. And so this mapping from the counterfactual world to the observed world is what the switching regression provides. Okay. That's what this sort of switching regression provides. So in the observed world, we are going to observe an outcome for everybody, but some of the potential outcomes are going to be missing for some groups in the observed world. Okay. But of course, this formulation of the potential outcomes framework then allows us to precisely define treatment effects of interest. And although generally we may be interested in a variety of treatment effects, the focus for difference in differences in terms of the parameter it's able to target properly is this so-called average treatment effect on the treated, called the ATT. Okay. So that's sort of a conditional treatment effect, and it's sort of conditions on who is treated. D equals to 1, right? So notice what it's doing here. For each unit I, what the ATT, which is called tau here, is doing is basically asking the question for unit I, what is the difference between their treated and untreated potential outcomes in period t equals to 1? So notice the subscripts here. Right? So it's sort of taking the difference between the treated and untreated potential outcomes in the post period, giving D equals to 1. So that's why this is sort of like ATT is a conditional average treatment effect where the conditioning is on D equals to 1. Okay. But if you're interested in DID, this is your target parameter. You are sort of mostly interested in the ATT. Okay. Now, without going into the details of the arguments, it will become clear that it will not be easy to simply look at data alone to identify or to be able to estimate this ATT, just given the data. So usually we have to pair data plus a set of assumptions, okay? And these assumptions are usually called the identification assumptions. And it is this combination that is able to allow us to sort of recover some sort of guess or estimate for tau hat, okay? So usually the sort of assumptions that are typical in the DID is to say, hey, because some of these potential, outcome quantities are not going to be observable, we are going to be making the usual assumption, which is called power trace assumption. There are also some additional assumptions like no anticipation that are maintained, okay? But if you maintain this power trace assumption and the no anticipation assumption, we can show in the standard case that, hey, you can combine your data in a particular way. So this quantity here is usually what's called the, so this is the DID estimand. You can combine your data in such a way that the quantity your research design DID will recover will become exactly equal to the ATT, right? Which is sort of the power of the assumptions, difference to differences. When you apply difference to differences, it's going to recover this estimate on the right-hand side of this equation, which, as you can see, is taking a double difference, okay? And you can take this double difference in a number of ways, in a number of two ways. You can first condition on D equals to 1 and take the difference across the two periods, and then condition on D equals to 0, take the difference across the two periods, and take the difference of those two differences, hence the name difference in differences, right? So if you compute this quantity, you end up with this DID estimate, which by these assumptions is going to be equal to the ATT, okay? So that's the logic here in terms of how we move from what we want to get with DID to the ATT, okay? So life is good up to this point if you believe in the DID assumptions, okay? Now, so this is the slide on identification, like how do you combine data to sort of recover quantities you care about? Now that you know that identification is assured and the DID estimate is indeed equal to the ATT, your next task is how do you estimate this DID estimate, right? Which is a task of estimation. So we know the DID can identify the treatment effect ATT, but how do we move from this right-hand side estimate to estimation, okay? Of course, you can simply do the sample analog of this quantity on the right-hand side. You can go into your data and compute them and take a double difference yourself manually. But as you all know, it has become very standard to use a type of a regression model estimated by OLS to recover the DID estimand, okay? And that regression model is usually called a two-way fixed effect specification or regression, and it usually takes this form where YIT equals to a unit fixed effect, which is alpha I, which is an indicator of basically a fixed effect for person I. Okay, then lambda t will be some sort of a fixed effect for time, which is lambda t. And you also have this sort of a product of the two, which gives you DIT. And the tau, notice the tau, the DID estimand loads on this multiplicative term. Okay, so it is interesting that once you specify a regression model of this form, you can then use OLS to estimate this regression model, and the estimator you get is a two-way fixed effects estimator, and that, of course, delivers the DID estimate, okay? So this is usually called the two-way fixed effects estimator. So that's kind of what is sort of the standard thing that's usually done. And so again, sometimes we are now moving gears to this DID, the staggered DID scenario. So sometimes treatment doesn't turn on at the same time for everyone, okay? So it is possible that some groups of units in your data are going to receive their treatment at different times, okay? And of course, even in that world, you might be tempted, or it may be natural to still use the same to a fixed effect specification. And the question for all the literature on staggered DID that evolved was asking the question, in this staggered adoption world, if you still compute your to a fixed effect estimator, do we have any hope that this to a fixed effect estimator is going to be recovering tau, right? So the question is, would the, basically with the probability limit of this guy be equal to tau, which is our ATT? So that's the question here. Is your to a fixed effect estimator here, as people may naturally do, able to recover your DID estimand, which is your ATT? Okay. And I guess most of us know that the answer is, generally no, sometimes yes, depending on the scenario. Okay. So I have presented already the challenge of staggered adoption. And again, to remind you, the key feature here is some units in your data are going to be receiving treatment at different times, okay? And for simplicity here, we are going to assume that once a unit eventually receives treatment, whatever time they receive treatment, the treatment stays on, right? So we're not going to cover all other cases at this time. The key challenge here is if a unit receives treatment at a particular time, which of your other units are going to serve as the control group, right? So this entire exercise is going to be an exercise in appropriately choosing your control groups, okay? So that's sort of what you want to have in mind. Are there any questions at all, or I can keep going on? All right. So to drive home this point, to get at this question about how to choose appropriate control groups, I want to begin with some notation here.
Sorry for interjecting, but I see a hand up. Kofi Ajabon. I'm sorry if I mispronounced your name. Yeah.
Thank you, don't worry. Please, what is exactly happened and in the two-way fixed effect we cannot use it for, with the two-way fixed effect we cannot use it to estimate difference in difference when we have a staggered group. Like, is that the question of the time the treatment starts? Is that because we have zero at certain time, which will multiply some of the group that has been treated at certain time, and or I don't know, is a mix effect the two-way fix will generate for us, or it will assign a certain kind of weight to the treated group, the first treated group. Yeah. So I don't know if you understand, but you can just take it like that. I'm not Anglophone, so thank you.
I completely understand. Thanks for your question, but that's the subject of the next few slides. So I hope to convince you that you can sometimes use two-way fixed effect, sometimes you cannot, but the answer to the question is what I would discuss in the next few slides. So if you hold on for the next 15 to 20 minutes, I think the answer will become clear. And if not, I can take the question again. But that's essentially the subject here. Can we use two-way fixed effects estimator or not? Can we not? And if we cannot, why? So that's sort of what I want to cover now. But it would be better for me to go through it instead of just providing a direct answer. So let me set some notation so that it will help me answer the question and also discuss what I have in mind. So it's always easier to have some notation so that we are all on board here. Okay. I borrowed this notation from Partha Deb's paper, which is a working paper, a really nice working paper I like in terms of how they set up the setup of this Staggered case. So imagine that you have a population where little g is going to index groups of units in your data. So you can think of this as countries. G can indicate countries, counties, or states, for example, right? So each unit is going to belong to one and only one of these groups, okay? So the little g here indexes groups, okay, whatever they are. Now, in this case, treatment is going to be occurring at the group level. So at some point, some of these groups or some combinations or collections of these groups are going to receive treatment, okay? And we are going to use Q to denote the period in which a group receives treatment or a set of groups receive treatment, okay? So if a collection or a set of groups receive treatment at time Q, we are going to say that they belong to a cohort C equals to Q, right? So a cohort is a collection of groups that receive treatment at a particular time. Now, each group is going to map exactly into one cohort, right? So, if group G equals to 2 receive treatment at period Q equals to 3, then they are going to belong to that particular cohort, C of 2. Okay, so each group is going to map into a particular cohort. Now, some units, we are going to take the case that there are never treated groups within the population that we have. So normally that's going to be indicated by this cohort indicator C equals to infinity, for example, at least from the notation I'm borrowing, right? So given this setup, then it is going to be now possible for us to define potential outcomes in this world. Now, notice that our potential outcomes now are going to be defined with respect to G. So it's the same YIT, notation we had before. And in that case, we simply said you had potential outcome defined in this way, 1 or 0. But in this case, potential outcomes are going to be defined, for G, which is going to be the outcome for a unit if their group G is treated or not treated, right? So G here if G belongs to this set of possible potential values for G, then they are treated at different times 1 to T, right? So we are going to define potential outcomes for every group with that in mind. Now, of course, similar to this guy here, we are also going to define a potential outcome for that untreated state in terms of the never treated people. Okay, again, we are still setting up notation for this to be clear. Now, notice that we can then say, for example, that what if we define a binary indicator that takes on 1 if you are a member of group G, okay? So RG is going to be an indicator for if you are a member of group G, okay? Now, if you're a member of group G, remember, multiple groups can be members of group G, right? So this set is going to collect all of the subsets of the data in terms of groups that receive treatment at a certain time and therefore belong to the same cohort, okay? This is useful because there is not simply just one ATT in this target adoption DID, okay? There are multiple types of ATTs that we can define. And that's why this notation is useful. So given that I have, covered the notation, then I will now present to you what the notation for the group time ATT is. So notice now we are calling the treatment effects group time ATTs, okay? And it is defined as follows. If you pay a little bit of attention here, again, we have to be conditioning. It's an ATT, so we are still conditioning on membership in RG, okay? So this is defined for groups of, for cohorts, okay, that receive treatment at a particular time. So notice this is taking the difference between the treated potential outcome for cohort G or groups of cohorts that receive treatment G, and taking the difference from the untreated potential outcome. Condition on RG equals to 1. So it has the same flavor. It literally has the same flavor. But notice that although it's not only defined for just one period, because this T can go from Q up to T. Q is the very first time any subset of groups receive treatment. So what this means is that we are going to define a set of tau GTs, which are ATTs that are specific to each cohort of treated groups for each period of their post-treatment period, right? So if you are a particular cohort, let's say cohort 2, and you receive treatment at T equals to 3, then we are going to define an ATT parameter for that particular cohort for time period 3, 3 plus 1, all the way to capital T, right? So there's going to be multiple ATTs here that we are going to be defining, but they are all going to be with respect to the group and the specific time. Okay, so this is an important difference, that here to the building blocks for our treatment effects within Staggered DID are these group time ATTs, tau GTs. So I want you to keep this in mind. You want to remember that what you are targeting within Staggered DID is the tau GT. Okay, and then when you get tau GTs, those are going to help you as building blocks to compute more aggregated treatment effects. Okay. So within the Staggered DID, there isn't just one ATT, there are multiple group time ATTs. Okay, and I cannot emphasize this enough. This is key. This is sort of the building block for treatment effects within Staggered DID. Okay, and in general, what is important here is that these tau GTs can vary across groups and can vary over time. So in general, we want to place no restrictions on the form of the tau GTs. They can vary across groups and they can vary over time as well. So they are going to be in general heterogeneous. Okay, so that's tau GTs for you. Now, to make this even more clear, suppose I pick a running example where I define my G to be 40 groups. So again, imagine that your population is such that every unit can be assigned to one of 40 groups. Okay. Now, suppose I have 8 periods, so T equals to 8. All right. Now, every row here is going to represent a cohort. So you can think of this as 4 cohorts here, and there are 3 timing groups. Okay. So, for example, on the columns, T equals to 1 is your first period, all the way to T equals to 8. Right. Now, I'm going to just for simplicity create 3 timing groups. So consider the cohort C equals to 3. Now, the cohort I'm defining as the early cohort here are the sets of units, okay, or the set of groups that all receive treatment for the first time in period T equals to 3. Okay, so a certain proportion of the 40 can be part of my C equals to 3, the early group cohort. Okay, and of course, once they receive treatment at period T equals to 3, they remain treated for the rest of the period. So treatment is an absorbing state. Now, there could be a set of these 40 groups that also receive treatment somewhere in the middle of the sample, called this C equals to 5, my middle group. So this is my second timing group. These people, the treatment indicator is 0, 0, 0, 0. And once you get to period T equals to 5, it turns on 1 for them. Okay. And then you can define a late treatment group as people who are here, C equals to 7. It's 0, 0, 0. When you get to this period, then they also receive their first treatment. Okay. So in this case, I would say there are 3 timing groups, although you sort of have 4 cohorts if you count this last cohort of C equals to infinity, which are people that remain 0 throughout the entire period of the data without ever receiving treatment. Okay, this running example, what you see on the board here, is what the typical staggered adoption DID setup looks like. Okay, but of course, this is just an example. So, in particular, you can have more of these timing groups instead of the 3 I'm presenting here. Okay, given your particular case. Now, so the challenge now that if we understand this setup here in terms of my setup here with my 3 timing groups, then the question is, what if I go and do 2-way fixed effects? Would that recover a meaningful treatment effect? Would that recover a meaningful treatment effect for any of these timing groups that are receiving treatment at different times? Will it recover any meaningful treatment effect? That's an average of all the treatment effects of all these groups. That's sort of the question here, right? Well, it depends on the comparison that a 2-way fixed effects, a standard 2-way fixed effect estimator makes, okay? If the standard 2-way fixed effect estimator is carefully comparing treated cohorts to cohorts that never received treatment, that seems to be a fine comparison. Okay, because remember that the definition of treatment effects here and the estimation requires comparing 2 groups, a treated unit and an untreated unit. So if the 2-way fixed effect estimator here is carefully choosing to do this comparison, that seems fine. If the OLS, the 2-way fixed effect estimator, is also choosing to compare later treated units, okay, so a later treated unit may be C equals to 7 here. If it's comparing them to groups that have not yet received their treatment, okay, so for example, you can compare C5 here to C7. Okay, later treatment, C equals to 5 to C7, group that has not yet received their treatment. If you make that comparison, that also seems fine. But if you compare a later treated unit, okay, as a treated group, to an already treated unit, this potentially seems bad, okay? Why? Because, for example, it almost seems like if you want to define the treatment effect for C equals to 7, you are counting as control some units that are in C equals to 3 and some units that are equals to C equals to 5, okay? If the 2-way fixed effect estimator is including some of these comparisons, then we may be concerned that the sort of weighted average of all these comparisons that a 2-way fixed effect delivers is not going to be representing any meaningful treatment effect parameter. Okay, so that's the concern here.
When the driver
can I go on?
Dr. Denta, please, there are some questions. I don't know whether you would want to take questions at this point.
I can take questions, please. What are the questions?
Yeah, Joseph, you can unmute yourself and ask your question there.
Yeah, so my question is on, so you mentioned that once a treatment or once a unit enters into treatment, it doesn't turn off, right? So what if we are facing a case where, so I'm going to use an example, right? You're working with data on concussions, right? Let's say student athletes who play sports and are likely to get concussion. So what if you have a student who gets concussed earlier, right? And then later on doesn't get concussed again, right? Because you are using like different periods, right? And in the first period they get concussed and enter into treatment. And then in the second period, they don't get concussed again, right? So in that case, treatment has turned off. What do you do in that case? Do you drop them or you just code them to be equal to 1 throughout?
Well, coding them to be equal to 1 throughout will be misclassifying their treatment status if they are not really receiving treatment in the later periods. Okay, so that wouldn't be what you want to do. There are some works that I can discuss later or provide reference that discuss cases where treatment can, turn off.
Okay.
That's a little bit, of course, that is a little bit more challenging for you, right? And the way that that approach is, which is the general point I want to make is here. You have to think about what you call a treatment effect and what you like. So one of the basic recommendations, even without referring to all of those people, is that sometimes you can catch your treatment or your data, okay, such that you only use post-treatment periods for that individual that don't include the period where their treatment is turning off. Because think of that person that you say is concussed in a period, let's say t equals to 1, or let's say t equals to 2, for example. If the person's treatment changes later on t equals to 5, and you still want to use data in that period, the question you want to ask yourself is, what does it mean to define a treatment effect for this person that is concussed in an earlier period? And if you include the data covering the period where it turns off, would you recover any meaningful treatment effects for being concussed earlier on? The answer is no. So for me, if the data allow the person to limit their sample period in a way that avoids the problematic period, I always recommend that first. Any other fixes that are available, and I have some that I can, share to the group later, it's usually going to require some additional assumptions to get you a definition of a treatment effect, right? You have to realize that none of this comes without a cost. You have to always think about your treatment and your treatment effect you care about. So if you care about treatment effect that is turning on and off and on again, that leads to issues for you in terms of how you want to define treatment and how you want to estimate it. So there's not a general prescription for what you do in that case. I always recommend the simpler cases, which is if I can get around simply by redefining my sample period such that I avoid the problematic periods, I do that first. That may introduce some sample selection, of course, but that's a trade-off you have to be willing to make, right? So there's not just one simple methodological fix to that problem. So I'd like you to take a view of, hey, if this is my case, let's carefully think of what is a useful treatment effect to define here, and what are the periods of data I need to get there. I'd like to always take that approach first and run into a methodological fix of the problem, because methodological fixes of any difficult problem usually involve inherently making some additional assumptions, okay, beyond the standard ones required just for the standard DID. I know that's not full a response to what you should do, but that should maybe get you started on how to think about that problem. And I can send some references to that can point to some suggestions for what you can do methodologically, but as I say, those don't come without a cost.
Yeah, thank you.
Yeah, so Kofi Ajapon, please, you can also ask a question.
Please, sir, you emphasize very soon that sometimes you have to shrink the data and work on certain part of the data. But in the real world, usually the data we have is what Joseph has already said. Because usually, for instance, myself, I'm working on drought data, and I see that at 1 year, as drought is a disaster, it can happen this year in a certain part of, for instance, Africa, and the next year drought will not happen anymore, and then the next year drought will happen again. So that is a kind of switching over period to period. So don't you think that if I have to shrink that data, I will lose a very large part of the data, or my data will be so restricted or just for one period, and there might not be too much data to estimate the average treatment effect on treated or something like that. Thank you.
Yes. But you've only highlighted that causal effects estimation is a difficult problem. That's basically what you are pointing out, right? There are two responses here. If you have such a data and such a scenario, your obvious solution is not only to say DID is my tool. And this is one of the points that I hope to make at the end. When you have a data set and you have a certain question in mind, you pose the question and you pose the treatment effect of interest, and you ask yourself, what methods are available for me to think about solving it? You don't simply say, I insist on using DID, okay? So yes, I gave the answer of the working with the data set and shrinking it sometimes in the context of necessarily saying you want to use DID, okay? But if you are open to other methods, there could be other things you can do. There are other panel data methods that are potentially available that also deliver certain kinds of effects or treatment effects, just not necessarily using DID. So one of the challenges with the DID literature is that everybody who has data in a question wants to apply DID. And then the whole exercise becomes, how do I constrain the DID toolkit to fit my data, right? Instead of saying, I have a question, I have a data set, what sort of methods are possible for me to answer reasonable questions? And sometimes that may lead you outside of the DID world, right? So again, I agree with you that the solutions are not perfect. And as I said, there are other methodological solutions that don't allow you to maybe stream the data in that way, but those also come with cost in terms of the assumptions you are willing to make. So my general prescription is don't feel stuck that you have to always use DID. And if you have to use DID and you are in that world, that's not a good usual case for DID if you are unwilling to make any other trade-offs, okay? So I would like you to take that more basic point as go back to your scenario. If I'm sure if we had a longer time, you and I have a meeting or a longer time we are discussing, here's my question, here's my data, we may be able to come up with other solutions to the problem without using DID. Okay, so I want to make that point clear that you are not married to DID when you are attempting to estimate a causal effect. Okay, and so I'll welcome a discussion on that further. But if I do, I may not get through my introduction to Staggered DID and what I want to be able to illustrate. And so I can take more questions, but I want to caution that I may not get through the point I want to illustrate.
Okay. What we can do is they can leave the questions in the chat so that we run through for the last bit of the session. Then we take whatever we can before the session ends. And if there are any pressing questions afterwards, they can email you. I think that should be fine then. Yeah.
Right. Because these questions are beyond the standard Staggered DID we are covering, today. So they are interesting, but we may not get through what I have. Because as you know, I'm on slide 15 of 40, so we may not get through it. Now, so as I'm emphasizing in this Staggered standard DID scenario, of course, the comparisons that the 2fx effect makes is what will determine if it's going to be a useful treatment effect you get in the end or not, okay? So I want to provide some intuition because I don't think this point is well known. There are potentially many kinds of decompositions of the 2fx effect estimate that are possible, okay, and that have been made in the literature. I usually like to use the Goodman-Bacon decomposition as a way to illustrate the concerns with using the 2fx effect estimator in this scenario, okay? Now, what Goodman-Bacon 2021 shows is that one potential decomposition of your 2fx effects estimator is that it's a weighted average of all the 2x2, all the possible 2x2 DID estimators that can be constructed from your data, okay? And each comparison may either be a clean one or a bad one, depending on whether it is in these first two categories or whether it's in this third category. Okay, and so that theory is sort of well laid out there. To sort of make the case clear, if you have, say, K, treated timing groups, okay, for example, then one type of comparison you can have in terms of the 2x2 DIDs within this framework is comparing each of the treated timing group with a never treated group. So that gives you K. So if you have K timing groups, you have K comparisons of this sort. But there are comparisons of this sort that can also fall in the comparing an earlier treated to a later treated, and there is K squared minus K over 2 of them. And then there are also comparisons that fall in comparing a later unit as treated versus an earlier one as control. And there's this number of them as well. So in total, there are K squared unique 2x2 DID comparisons that are potentially that can be potentially constructed from your data in this target world. Okay. Now, I provide the example again in my case where I have K equals to 3 timing groups. Remember, I have K equals to 3 timing groups. This is timing group 1, timing group 2, timing group 3. Each receiving treatment at different times, okay? And each of these can lead to then 9 distinct DID comparisons that you can make in this case, okay? And essentially, your 2fx effects estimator he shows is recovering a weighted average of all these 9 distinct 2x2 DID comparisons. To be more clear, the type 1 of the kind of comparison that it's doing is using a treated cohort or timing group versus a never treated cohort. Now, again, K equals to 3 in my world here, right? And so, again, as I said, there's going to be K equals to 3 comparisons of the first type, which means here, type 1, type 2, type 3. Okay? And what are the 3? You are comparing an early, a middle, and a late treatment timing group, always with a never treated group. Okay? That's the first one. This is a clean type of 2x2 DID, and that should not bias the weighted average that the two-way fixed effect estimator is doing. You can also end up in a world where you have an earlier treated cohort being used as a treatment group and a later treated one being used as a control group. And these are also fine. And as we said, there is K squared minus K over 2 of them, which is equal to 3 of such comparisons. So for example, I'm comparing the early treated to the middle, the early to the late, and the middle to the late. And all of these are fine because in this case, the control groups are never groups that were already previously treated. And there's 3 of these as well. And then the problematic comparisons are of the last category, where a later treated unit or timing group is being compared to an earlier one. Okay? Now, if you do this, there are 3 of those kinds of comparisons as well. You compare middle treated using the early ones as a control. You again look at a late treated timing group and use the earlier one as a control, or a late and middle one as a control. In all of these cases, these control groups have already received treatment by the time you are making the comparison, right? And these 3 types of comparisons are also part of the weighted average that the two-way fixed effects estimator in this case uses. Okay. So again, to make this more clear, this third comparison is what potentially contaminates the DID estimate. Remember, I say potentially here, because again, the issue is not that automatically the two-way fixed effect estimator delivers a wrong DID estimate. Okay, that depends on this. That depends on this comparison here in your 2x2 DID. Okay, so if you use an early cohort as a control that has already been treated, then the change, okay, represented by the control group, also includes the evolution or the change, the treatment effect of that group. Because if treatment effect is changing across time, then the earlier treatment group that you are observing later, its treatment effect has already changed and contaminated the outcome as you are using as a control group in that later period. Okay, so this can potentially create the problem. All right, and so in particular, when does the two-way fixed effect seem to work? Well, theoretically, the bad control problem may not arise if you are in a world where treatment effects are homogeneous. Okay, all the tau GTs are equal to tau for all G and T. Okay. Now, if you are in a world where treatment effects are heterogeneous, of course, where tau G may be different across G and T, then in that case, that third comparison, that third group of comparisons may bias your two-way fixed effects, weighted average, such that the quantity you end up with may not be equal to your DID estimate. So in that case, this is the case where the probability limit of the tau hat two-way fixed effect estimator may not, converge to your DID estimate. Okay, so then this is problematic in those particular cases. So this is a case that may be different on a case-by-case basis, right? Depending on the scenario you are in. But if you take the view that treatment effects are generally heterogeneous, then this may usually be the case, right? So I can, in the interest of time, I have, I have a way to. I'm in the interest of time. I think I'm going to, since I provided intuition already, I'm going to skip the theorem, the formal statement of the theorem. But I welcome you to read Goodman-Bacon 2021. That shows you in particular what the weighted average looks like. Okay. So the beta 2 fixed effect in his decomposition is equal to this weighted average that is on the right-hand side here. And again, that's the average of all the 2x2 DID estimators. Okay, so I welcome you to take a closer look at that sort of decomposition. And in particular, the weights. So one thing about the weights in that decomposition in this case is that they depend on the size of the subsample that are being used for the estimations of the 2x2 DID. And it also depends on just the variation, okay, in the treatment variable, okay, in the particular window that you are using for the comparison. So in some ways, the question is, does that sort of weighting that the to a fixed effect estimator adopts here, does the weighting that it adopts here, is that weight anything the researcher cares about? And the answer may be no. Okay. So again, in the interest of time, again, he does a pretty good job of, again, demonstrating why, and I'm kind of putting it on this slide again for you, is if the p-lim of the to a fixed effect estimator is in general not equal to the DID estimate, then what does it recover if we convert everything in terms of potential outcomes? He also shows that actually it can recover some sort of ATT. That kind of ATT is variance weighted, plus a combination of two things, okay, which he gets into detail for. And if you assume homogeneous treatment effects, then of course this term can go to zero. And if you assume a common trends or parallel trends, this term can also go to zero. Then in those cases, your probability limit of the two-way fixed effect estimator may be equal to some sort of an ATT, okay? But remember that ATT is variance weighted, okay? So that's sort of what, we sort of get from this scenario. So this is sort of the intuition, and all of the solutions, so I'm going to skip it. So all of the solutions that have been developed for DID is trying to find cases where you can build or construct estimators of your group time treatment effect such that when you aggregate them, it will deliver a credible, meaningful causal effect. Okay, so the answer to the question which someone has is, what's the problem with the two-way fixed effect estimator? The problem is that you may be applying it to a model that is too restrictive. And in particular, in that restrictive model, if you still impose homogeneous effects, your two-way fixed effects may be fine. Okay, but if you're in a world where effects are heterogeneous, but you still choose to apply two-way fixed effects to a restrictive model, then that two-way fixed effect estimator is going to fail to deliver you an interesting treatment effect. Okay, so I like to end sometimes with this motivation, with this quote, and again referencing that question someone asked: what is wrong with the two-way fixed effects? Nothing is wrong with it. And this important quote by Jeff Woolridge is important. There is nothing wrong with the two-way fixed effect estimator in and of itself. It's simply an OLS estimator applied to a particular model, and the model you apply it to is important. If the model is too restrictive, the two-way fixed effect estimator may fail. If the model is flexible enough, the two-way fixed effect estimator may still work to deliver your DID parameter of interest. So again, the two-way fixed effect is just a tool. Your DID is the research design. So you have to focus carefully on thinking about the design you have, the nature of your data, the nature of your treatment effect adoption, and think about that more carefully. And even beyond that, think about whether DID is the appropriate research design for your case. Okay, so there's nothing necessarily wrong with the two-way fixed effect in and of itself, in general. And again, this is an important point that people have missed, which I put here because one of the people that has worked a lot on this, as some of you know, is Pedro. And he has this t-shirt that says, your two-way fixed effect estimator is not a problem. It's just not equal to DID in every case. In fact, it's not. Okay. So I want to end with a simulation to quickly demonstrate the potential issues that can arise that I've discussed theoretically. And in order to do that, I will simulate a very simple case. Again, my running examples, I have 8 periods, I have 40 groups, I have cohorts that receive treatment at particular times. And so I first generate an untreated potential outcome path, which is a very simple path. And then I also generate a treated potential outcome path for every G in the data, okay, every cohort in the data. And that path is very simple, right? You take the untreated one and you add a particular treatment effect path to it. And the path is very simple, right? It's a very linear path. So the only source of the heterogeneity here is just how long you've been exposed to the treatment. So if you are exposed longer, then your tau GT for that group is going to be bigger. So it's a very simple sort of like treatment effect path. So again, the observed outcome that the person observes in the data takes this form, okay, in the data. So let me give you graphically what that means in terms of visually. So In this case, I'm thinking that the first, this period is the pre-period. It can extend to t equals to 1, 2, and t equals to 1. So that's not being shown here. But no treatment effects are computed for any period t equals to 2 or t equals to 1. So for the early treated cohort, they receive treatment when t equals to 3, right? And I'm simply saying in that period, t equals to 3, where they receive the treatment, this is the value of their tau g, okay, which is equal to cohort 3, and period equals to 3. So this is the tau gt. For these people, is 1. When you go to the next period, t equals to 4, they are tau gt. Remember, these are group time ATTs. So every period has 1. So tau gt for this period is 2, is 3, is 4. So I'll just allow it to grow linearly over time. The middle group is also of a similar path. They received their first treatment in period t equals to 5. So the first tau gt for them in terms of a treatment effect is in period 1. Right? So you can see that depending on the group and time you are in, there is an ATT for that period and that ATT for that group. Okay, so there are multiple treatment effect parameters in this case. And the late timing group or cohort only has 2 of those tau GTs for this period and for that period. Okay, so this is sort of the setup. If you want to view it, this is sort of what the paths look like, the tau GTs plotted by time. Okay, it's just sort of linearly growing in each period. So there's treatment effect heterogeneity here across time. So clearly you know that this is a case where potentially the 2A fixed effects estimator may be biased for the ATT. Okay. Now, if you have multiple tau GTs in this form, what is the one way in which you can summarize all these many tau GTs? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 tau GTs in my experiment here, 12 of them, 12 ATTs, 12 group time ATTs. So how do I summarize them into one quantity in the DGP? Well, you can do a simple average, which is what I've done. If you do the simple average, the value of the simple average of all the 12 tau GTs is about 2.83. If you apply the standard, I should say standard, to a fixed effects estimator to this data set that I've created, you end up with an estimate of 1.55. Okay, so clearly that is biased downwards, and of course that bias downwards is being driven by those bad comparisons we talked about. So this is one example where the 2A fixed effect estimator applied in the standard way may not yield reasonable results. Okay, so now looking ahead, this presentation only focused on diagnosing what the problem is and understanding why we may think 2A fixed effect fails in some cases and doesn't fail in other cases. All right. And many solutions have been presented to people. Many solutions are presented. And I'm told the next iteration of this will be discussing some of those solutions, but many have been presented. All of them, I think, have the same flavor where what they hope to do is, can I reasonably estimate group time ATTs, the tau GTs, the 12 that I have? Can I propose a method that estimates my 12 tau GTs? And if I can I aggregate them into one interpretable summary parameter? Okay, so all of the sort of like the solutions are going to have this flavor. Okay, so next time we'll cover some of these solutions and how they develop estimators for these 12 these tau GTs and how they aggregate them into one treatment effect parameter. Okay, so I'll stop here since we are almost at the end.
Thank you so much. I think I'll read out the very one question we have in the chat. So someone was asking, does it apply for repeated cross-sectional data or just panel?
Yes, this presentation applies to both, and the notation is flexible enough to be adapted to both cases. And then some of the solutions that are proposed apply to panel data, some apply to repeated cross-sections as well. So this general presentation applies to both.
Okay, thank you. I don't know if any other person has a question before we take some few announcements and close.
I just want one more. Can you hear me? Can you hear me?
Yeah, we can
Yes.
hear you, but there are some echoes. Yeah. Please, we can hear you. You can go on.
Yeah. Okay, let me write the question because I myself can't hear myself. Yeah. Yeah.
Okay, that's fine then. Well, whilst we are waiting for, okay, there's a question that says, that is asking if you have data where one unit stays treated all the time, has no pre-period, is it okay to drop that? And if yes, does this affect your estimation or results?
This is a classic case where you have an always treated unit. Yes. Again, I am always of the view that the simpler solutions are better solutions. Okay. So in a lot of scenarios, when I encounter a scenario where some units have always been treated, I sort of remove them from my estimation sample depending on the question. You see, you have to ask yourself, given the question I have, okay, does it make sense that some of my comparison units are going to be units that have remained already treated before my sample period started? You have to ask yourself, is that a right counterfactual you want to include in estimating your treatment effect? There's not one solution to this problem. If you include them in it, it has some implications for how to interpret your treatment effect parameter. If you remove it, it also has implications. But I think the implications for removing it are easier to justify and understand than those for including it. Okay. So in general, I start with the simpler solution, which is I remove those people who have remained always treated. Okay. Now, I'm not saying again that's the only solution. As I've told you very clearly, the search for what is right, quote unquote, is usually elusive. The question is, given my context and my scenario and my data, if the treatment effect parameter I seek to estimate is particularly of this form, does it make sense that part of the comparison group is going to include a group that has always been treated? In most cases, you might say no. There's a case where somebody may say yes, and they have the onus of justifying why it makes sense in those cases. Now, if you remove them, somebody might say your treatment effect is no longer very generalizable, is less externally valid. Sure, but that's a point you can address in the discussion of your paper. Okay. So you just have to be you just have to be careful to say this is the treatment effect parameter I care about, and including this doesn't help me or helps me. Okay. And it's just
Thank you so much.
when it says data removed, I see a comment that I try to include them and data remove them. It may remove them telling you that ECS DiD framework doesn't allow for always treated units to be part of their estimation routine. That's a choice the developer of that method DiD made. If you don't like it, then you have to find a different estimator or a framework that allows you to include it. So it's not a problem of Stata. It's a problem of your question, your treatment effect, and the tool you've chosen to answer it.
Thank you very much, Professor Dente. It was very insightful. I think I could say, just correct me if I'm wrong, a case where you discover that probably all the estimator available could not solve your problem, you could also develop your estimator. Is that correct?
It is always on the table. Yes, it is always. In fact, not only develop your own, you can completely abandon difference in differences. I mean, there are many choices. Let's not make the case as though DiD is something that we are all married to. Okay, as economists or researchers, we are not married to any tool. We are married to the questions we want to answer.
Yeah, thank you, sir. Appreciate it.
Okay, thank you so much, Dr. Dente. I think we're going to pause the questions, and if you have specific questions, his email would be made available so that you can directly reach out to him. The only announcement available is that we are going to roll out a call for papers. So if you have any work in progress kind of paper you would want to present and seek the view of others on in order to develop a paper, kindly keep an eye on your email and apply when we roll out. Thank you, everyone, and we'll see you, I think, on March 20th. Bye.
Yeah.
Hmm.
Thank you very much for the invitation. I think it was very insightful questions, and I hope next time I'll see if I'll address some of the turning on, turning off questions that have come in the description of the solution next time. I think all of that is useful, but as I keep trying to point out to people, the fascination of thinking of the methods first is just mind-boggling to me. It's like you have a question and then you say, what can Stata offer? So in some sense, it has led to this sort of, so even though I took the opportunity to do this, and it was, of course, very easy for me to do, and I hope it's helpful to some. I did it not because I'm excited about it, because I don't want to be talking about DID every time, but I did it because I feel like I should contribute and let people know that, they should not feel